Imagine a place where time slows down, light bends, and reality itself breaks apart. A place so powerful that not even light, the fastest thing in the universe, can escape. These cosmic monsters lurk silently in the depths of space, black holes. But to truly understand them, we need to journey through space, from our own cosmic neighborhood to the very edge of the known universe. Today, we're going to take you on an epic voyage, across galaxies, through wormholes, and into the heart of a black hole itself. Buckle up, because this ride will blow your mind. To understand them, we must first measure the stage they play on, the universe itself. We look up at the night sky, a glittering canopy of stars, and feel a sense of wonder. But what we see is just a tiny fraction of what is out there. Our journey begins on Earth, a tiny speck of rock and water in a vast dark ocean. From there we'll travel outward, to our galaxy, across clusters, and into the webs that bind the cosmos together. Before we dive into the abyss of black holes, let's appreciate the vastness of the universe. We can travel to the moon in a few days, a journey that feels immense. Beyond the moon lies our solar system, a family of planets orbiting our star, the sun. The furthest planets are so distant that spacecraft take years to get there. Pull further back and our solar system shrinks to a pinprick against the Milky Way. Our sun is just one of hundreds of billions of stars in this spinning disk. Imagine every grain of sand on every beach on Earth. That's roughly the number of stars in our galaxy. And the observable universe? 93 billion light-years across, containing 2 trillion galaxies. Galaxies form filaments and sheets, a vast cosmic web of glowing filaments and dark voids. Within this unimaginable scale, black holes exist everywhere, silent, invisible predators. They bend space, warp light, and feed on gas and dust. The darkest objects in the universe can create some of the brightest phenomena we've ever witnessed. At the centers of galaxies, supermassive black holes anchor cosmic evolution. Our journey outwards has set the stage. Next we learn how black holes are born. So, what exactly is a black hole? At its core, a black hole is a region of space where gravity is so intense that nothing, not even light, can escape. The boundary around it, where nothing can escape, is called the event horizon. This is why they are called black holes. They do not reflect any light. When a massive star, much bigger than our sun, runs out of fuel, its core collapses under its own gravity. The outward pressure from fusion suddenly fails, and gravity wins. The collapse triggers a spectacular supernova, blasting the outer layers into space. But the core may continue collapsing until a black hole is born. At the center is the singularity. Around it, the event horizon and the glowing accretion disk. Stars and gas spiral into the disk, releasing enormous energy as they fall. When supermassive black holes feed actively, they can produce brilliant jets and quasars visible across the universe. First, stellar mass black holes, born from single massive stars a few times the mass of our sun. Next, intermediate mass black holes, the missing link, hundreds to thousands of solar masses likely forming in dense clusters. Finally, supermassive black holes, millions to billions of suns found at galaxy centers. From small but dense stellar remnants to galactic anchors, black holes span an incredible range of scales. Next, what happens when you get close? Time slows, light warps, and space itself becomes a dangerous place. As you approach the event horizon, gravity becomes so extreme that stars stretch and warp. Light bends around the black hole, a cosmic funhouse mirror, time dilation. An hour for you near the horizon could be thousands of years outside. Imagine orbiting a black hole for an hour while civilizations outside age centuries. For you, seconds pass. For the universe, epochs unfold. We measure small versions of this effect today. GPS satellites need relativistic corrections. Near a black hole, gravity isn't uniform. The side closer is pulled far more than the far side. Falling feet first, your feet are stretched stronger than your head. You would be elongated like spaghetti, atom by atom, until you are torn apart. For small, stellar mass holes, tidal forces near the horizon are extreme. Spaghettification happens before you cross. For supermassive black holes, the horizon's pull is gentler. You might cross intact only to be torn later. At the center lies the singularity, a point of infinite density where our laws of physics break down. Einstein's general relativity and quantum mechanics both fail to give sensible answers here. Some theories suggest a Planck star or quantum foam could replace the singularity, but we simply do not know. What happens to the information that falls in? Does it vanish, or is it preserved? This is the black hole information paradox, one of the deepest problems in physics. Some propose that information is stored at the horizon like a hologram of what fell in. Mathematics even allows hypothetical white holes and wormholes, tunnels connecting distant points. In theory, falling in one place could eject you somewhere else or into another universe. But reality is probably harsher. Standard wormholes are unstable and would pinch off, and tidal forces would likely destroy travelers. To build a traversable wormhole, you would need exotic negative mass matter, which we have never observed. Some even speculate the Big Bang might be a white hole event, stimulating but currently unproven. Wormholes and white holes ignite the imagination, but remain mathematically tantalizing and observationally unsupported. Now let's meet one of the most extreme black holes known, TON 618. The biggest black hole ever found, TON 618, is a supermassive monster over 66 billion times the mass of the Sun. To put that in perspective, our Milky Way's Sagittarius A is about 4 million suns. TON 618 dwarfs it. If placed at the center of our solar system, its event horizon would swallow Neptune and the Kuiper Belt. TON 618 is also a quasar. It shines with the light of trillions of suns as it feeds. Its sheer size challenges how black holes can grow so fast in the early universe. Accretion limits and mergers are part of the puzzle. Astronomers debate whether extraordinary growth mechanisms or exotic physics are needed. If a black hole orbits a normal star, it steals gas. That gas forms a hot accretion disk that shines in X-rays. X-ray telescopes detect this radiation from space, revealing otherwise invisible black holes. At our galactic center, we watch stars whip around an unseen mass, proof of Sagittarius A. In 2019, the Event Horizon Telescope linked telescopes around the globe to form a planet-sized instrument. They combined radio waves into an image, not of the black hole itself, but of its shadow. The glowing orange ring of M87 became our first direct view of a black hole's silhouette. We also listened to spacetime itself. LIGO detects ripples produced when black holes merge. Merging black holes generate gravitational waves, tiny distortions in spacetime we can now measure. Each detection reveals masses, spins, and the dynamic lives of black holes. Combining images, simulations, and gravitational wave data tightens constraints on black hole physics. Together, these tools let us test general relativity in the strongest fields accessible. As our measurements improve, so do our ideas, including whether black holes might one day be harnessed for energy. Black holes are the most efficient energy generators in the known universe. Where fusion converts 0.7% mass to energy, accretion onto a black hole can convert up to 40%. A future civilization could build collectors or megastructures to harvest that output. The Penrose process suggests extracting rotational energy from a spinning black hole via the ergosphere. Split an object in the ergosphere, one falls in, the other escapes with more energy than the original. Over eons, such processes could power civilizations on unimaginable scales. These ideas are speculative, but they spring from real physics and our growing observational power. From radio arrays to gravitational wave detectors, we've built tools to probe the extremes. Our curiosity drives invention. The next generation will push further into these mysteries. Black holes are destructive and creative. Graves of stars, cradles of galaxies, and laboratories for the laws of nature. They challenge our understanding and invite us to look deeper. If you enjoyed this journey beyond the stars, don't forget to like, subscribe, and share, because the universe is just getting started.